Welcome friends. We have come to the part 3 of aldehyde and ketone. As I promised earlier in part 1 of aldehyde ketone that in the reaction mechanism of aldehyde and ketone, canazaro, aldol or acetal or condensation reaction in the acidic medium are the most crucial. More or less in every NEET, JEE Mains or advance, the various structures, they will form various structure to form or to ask this aldol mechanism or canazaro or acetal mechanism. Even condensation mechanism is there. So to identify the canazaro mechanism, at first let us start with canazaro mechanism. I have discussed the canazaro mechanism, canazaro reaction, but not the mechanism. Now the canazaro reaction mechanism is integral part of the aldehyde or ketone. Ketone doesn't give any canazaro, but aldehyde gives canazaro, and canazaro reaction is the integral part of the reaction mechanism of aldehyde. The condition is 1. Aldehyde with no alpha carbon or alpha H will perform the canazaro reaction. How? Let us consider the formaldehyde. One formaldehyde reacts with another formaldehyde in basic medium, that is alkaline medium. At first, we have to know that due to resonance, this pi electron comes over oxygen and the carbon actually stands with single bond oxygen. Now the first step 1. The step 1 reaction is very slow. The hydrogen part of any one formaldehyde splits and it comes as H minus. It is called hydride shift. It is called hydride shift. Since the double bond pi electron comes over oxygen, here comes the positive tail or partial positive charge. The hydride comes and attacks this carbocation zone or partial positive charge of the carbocation, and the remaining structure lies here. The first aldehyde or formaldehyde is with this one, and the second is H with C. Another H comes as hydride, another H comes as hydride, the one H already there, and single bond O minus. In this case, since this carbon atom also by resonance gives the partial negative charge over oxygen, the medium OH minus, this is step 2 actually. This is the step 1 hydride shift, and this is the slowest one. This is the slowest step, because here no OH minus ion in medium takes place, and technically it is the SN1 or slow reaction. But in second step, the concentration of the OH is also involving, and the reaction mechanism or reaction rate becomes faster. So in second step, this is step 2, the OH minus ion in the medium or is present attacks the carbon. As a result, this aldehyde becomes HC single bond O and OH, where the partial negative charge or electron will come again into this bond to form the double bond. Here the double bond forms and it becomes the acid. HC double bond O OH. The acidic part subsequently gives H plus into the medium. The acid part, the acidic H part, the acidic H plus subsequently gives H plus ion into the medium. And it attacks the previously formed alkoxide ion, that H plus. So this part forms H, C, H, H and OH, that is methanol, and this forms the formate ion. Formate ion looks like here the H is not present and O minus. If we use NaOH into the medium, the Na plus subsequently attacks the O part and forms the HCOOE. So it is the sodium formate and it is methyl alcohol. So the net result is HCOONA and CH3OH. Here is a rule. Rule is always the lighter aldehyde, that is not heavier, that is not bulkier, like formaldehyde. The always lighter aldehyde will form acid, salt, and bulkier one, the bulkier aldehyde, will form alcohol. Remember this criteria very, very carefully. So, if in case of mixed Cannizzaro, if there is mixed Cannizzaro reaction, let us quick have a look of comparative examination. The aldehyde is benzaldehyde and the aldehyde is formaldehyde. Now this is resonating structure, benzene nucleus. This is stable. So this cannot undergo hydride shift, but this can undergo hydride shift. As hydride shift H minus, it will attack here the carbocation zone because this electron comes over oxygen. And as a result, the benzene part will form CH5CO minus H and H. Subsequently, this part will form HC double bond. This is the step one. This is the slowest part, as I discussed earlier. The second part is the OH minus ion into the medium attacks the carbocation part. Here comes the oxygen, over the oxygen the electron, and it forms the HCO and OH, that is formic acid. On the other hand, this acid part or this acid gives H plus, subsequently attacks the alkoxide ion as a result of the combination of two different aldehyde. As a result, the combination of two different aldehyde like C6H5CHO and HCHO, we will get into the OH minus medium. The bulkier aldehyde becomes C6H5CH2OH and the lighter aldehyde becomes HCOON, because in our medium, let us consider it is NaOH, let us consider it is KOH, then in case of KOH it will form HCOK or sodium formate, calcium formate or potassium formate. Now, if these are the mechanism of Cannizzaro, rule is lighter aldehyde. Always think of the question, lighter aldehyde will form acid, bulky aldehyde will form alcohol. But the alcohol will be always 1 degree alcohol. These are the mechanism of Cannizzaro reaction. Now we will come to aldol reaction. aldol reaction or ketone reaction. In case of ketone, it is ketone. In the case of aldehyde, it is called aldol reaction. Now, as I am giving the name aldol reaction, it is of two types. It is of two types. One is base catalyzed. One is acid catalyzed. Means that in medium the ion is OH minus and acid catalyzed the medium is H plus. In case of aldehyde group, the acid catalyzed reaction takes place. In case of base catalyzed, the ketone group takes place. That means C double bond O, R and at first we will discuss about this acid catalyzed group, acid catalyzed reaction. First condition is aldehyde with alpha H or alpha C. Previous one was no alpha H and no alpha C. Here is the main difference between canazine and aldol. The aldehyde must contain alpha hydrogen. Now, in case of, let's say, CH3 CHO. CH3 CHO, the oxygen takes as usually the electron. The oxygen takes as usually the electron and another aldehyde alpha H with the aldehyde group. The alpha H plus splits from the aldehyde. The remaining aldehyde becomes CH2 minus tail or carb anion. The H plus combines with the OH minus. So it is, we are discussing base catalyzed. The OH minus medium and becomes water. So here comes the carb anion and here comes the carb cation. The electrostatic force between the carb anion and carb cation forms beta hydroxy compound. How it looks like? CH3 C O minus charge, CH3 C O minus charge, H, and the second part is CH2 CHO. Later on, this H2 splits into H plus and OH minus. The H plus attacks into the O minus part and forms, this is the functional group. This one I am showing it in a different color. This is the functional group. This is alpha H, alpha carbon or alpha H, and this is beta carbon or beta H. So the H plus attacks the O minus to form OH, and this is called beta hydroxy compound. Beta hydroxy compound. As I have said earlier, that beta hydroxy is highest prone to dehydration. It is highest prone to dehydration. Technically, it is very unstable. And taking one alpha H, it releases one water molecule. So, consider this reaction mechanism, that the mechanism is the H plus actually working, but the OH minus ion remains into the medium. So that it again reacts with one alpha H to form the water. The H plus attacks beta hydroxy, attacks to form beta hydroxy, and beta hydroxy leaves one water to form beta alpha unsaturated compound, that is CH3, CH, double bond CH and CH. So this is beta hydroxy, alpha beta unsaturated aldehyde. Alpha beta unsaturated aldehyde, you may call it 2-butynyl according to IUPAC or proton aldehyde. And again I am mentioning croton aldehyde, which I have mentioned in earlier classes. So this is croton aldehyde. So the structure, ultimate structure is CH3, CH, double bond CH and CH2. This is croton aldehyde. Or you can say 2-butanol. So this is the part of, you may say it, base catalyst. Now the base part is this acid catalyst. The base part is remaining within the medium. Now in case of ketone it differs. In case of ketone, we know that due to tautomerism, expected that the K-zero and half part of the aldol is clear to you. Now friends, we must look to the CH3 whole to C double bond. Here it tautomerizes to form CH2 double bond CH, OH and CH3. So this is ketone part and this is enol part. So they always interchange themselves into keto-enol tautomerism. If there is any ketone group, there will be tautomerism. It may call as tautomerism. Now, the acid catalyzed. Previously, we have discussed base catalyzed for aldehyde. Now we will discuss acid catalyzed for ketone. So ketone, one ketone lies as like this and another ketone lies as is this. Now, how the reaction mechanism goes on in case of ketone? Let us consider that the acetone is the least molecular weight ketone. Acetone is presently like this one. This acetone will react with another enol form of the ketone. This acetone will react with the enol form of the ketone. The enol form of the ketone is like CH2, this CH2 double bond CH, OH and CH3. But forget that. In medium there is H plus. In medium there is H plus. As it is, I already told that this is acid catalyzed. Now this H plus into the medium will act over this oxygen as this double bond becomes single bond, and this, due to resonance, this H plus can attack the O minus ion and forms CH3, CH3, C and OH. Clear? So at first this CH3 and OH, here the carbocation part or positive tail remains. In next instance, when the CH3 C positive tail OH reacts with one enol form, that enol form is like CH2 double bond C and remaining the OH with CH3. This is enol form. The carbocation part will be attacked by this pi electron charge cloud. So this electron will attack this carbon. Here it is OH. Now, according to that part, this is anionic due to this double bond pi electron, and this is cationic or partial positive charge. As a result, the structure will be CH3 will be intact, and the COH part will be intact, but the CH2 part, as the pi electron charge cloud attacks here, it makes it single bonded, and the rest part is CH2, CO and CH3. The rest part is CH3, CO, CH3. How? Because this H part as H plus attacks the first step, the step 1. As here the H comes out, this makes the oxygen double bonded and makes the perfect area ketone. So this is the functional group. I am showing it a different color. This is the functional group. This is the alpha H or alpha carbon, and this is beta carbon. So technically this is beta hydroxy compound, and it is also called as not aldol but ketone. This is also called ketone condensation. I have mentioned that this beta hydroxy compound is very much prone to dehydration. It will take alpha H and leaves one water molecule to form the structure like CH3, CH3, C, double bond CH, CO and CH3. This is the ultimate structure which we usually call as mesitile oxide. So this is acid catalyzed. Why? The enol part H plus attacks at first one ketone to form the OH part with positive del carbon. Next instance, the pi electron charge cloud attacks the positive del of the carbon and makes the carbon-carbon bond, new carbon-carbon bond with the OH remain intact, so that the beta hydroxy compound forms. The H part leaves so that the remaining part becomes ketone, and ultimately beta hydroxy compound forms. The beta hydroxy compound subsequently leaves water molecule, as it is very much prone to dehydration, and forms mesitile oxide. Clear? This is base catalyzed and acid catalyzed. This is acid catalyzed for ketone, and previously there was base catalyzed for aldehyde. These are the very important mechanisms. Other than this mechanism, there are certain reactions, like if there is any carbonyl group, like the example is acetaldehyde is like this. It reacts with two molecules of ethyl alcohol. Since it is acidic, it reacts with H plus to leaves one water molecule, and it forms acetal. CH3, CH, OC2H5 and OC2H5. As we have discussed earlier that the haloform reaction, look at this structure. It is called acetal. Look at this structure. Here there is no ketomethyl group, but since ethyl alcohol shows haloform, and as well as acetaldehyde due to ketomethyl group shows haloform, only ethyl alcohol as 1 degree alcohol shows haloform, and acetaldehyde due to ketomethyl group shows haloform. This further splits up in medium, like I am giving the medium NaOH and I2. Into the medium, they will be separated to form acetaldehyde and ethyl alcohol. So, out of so many molecules in aliphatic organic chemistry, this acetal, though having no ketomethyl group or no secondary alcohol group neighboring the methyl group, it will perform the haloform reaction, and both will give ultimately CHI3 with the subsequent acid salt, that is HCOOE. So they are performing, that means they are performing CHI3 and HCOOE. They are performing actually. This group doesn't contain any ketomethyl group, but still it undergoes haloform reaction. So this is, if this is called acetal, in case of ketone, like this is acetone, and like this is acetone, it is reacting with alcohol, like ethyl alcohol, to form ketone. At first it was acetal, then it was ketone. The CH3 part remain unchanged, but the two bonds will hold OC2H5 and OC2H5. This is called ketone. So one is acetal and other is ketone. So in case of this is ketone, in case of this is acetal. So the water part will come out from ethyl alcohol to form the ketone part. Remember this very clearly. For ketone it is ketone, for acetone it is acetal. Here it is also do not have any ketomethyl group. So it will also positive to haloform test. That is, they will give iodoform EOLO solid. That is how you can be distinguished. You can be asked to distinguish this type of molecule with formaldehyde. Now this type of molecule is undergoing haloform, but formaldehyde having no ketomethyl group will not form any haloform test. So we have discussed some of the real good mechanism of or important mechanism of aldehyde and ketone regarding K-zero and aldol. Now this is very important that if this is formaldehyde and positive tail, the positive tail mode will form, the mode will be K-zero. That means any structure they are given, like the aldehyde, benzaldehyde with NO2. The NO2 group has minus I effect. It will pull the electron from carbon, and carbon has more positive tail, and therefore that reacts more faster K-zero. So K-zero, in case of K-zero reaction, minus I enhances the K-zero, whereas plus I decreases K-zero. This fact is very important for any comparative examination. You will be given many structures, like you will be given CHO and paramethyl, that is paramethyl benzaldehyde. Paramethyl benzaldehyde has plus I effect. Here it is plus I, here it is minus I. So this will give faster K-zero and this will give lesser K-zero. So this sort of the name reaction. The name reaction is actually are given into predicting trends, that which one will be given more K-zero, which one will be given more aldol, or which one will be given less K-zero or less aldol. So we are completing this class regarding K-zero and aldol. We will discuss the aldehyde, that is acetaldehyde and formaldehyde, in our class, in our syllabus, along with some condensation reaction with H2SO4 medium. You can see in your book, in any textbook, but we will discuss the mechanism in our third class. So today we are ending this class, and thank you.